we're starting the recording for today's class. Just before I get into the material directly, I would like to give you a small information that in your textbooks, you can find these stuffs in the chapter name that is medical imaging. Where are those stuffs? Books, downloads. So yeah, this is the index, and you have a chapter called medical imaging. This is the chapter that we are gonna pick up right now, which earlier was said to be remote sensing. Why was it called remote sensing? I'm gonna talk about that a little bit, and then we can we'll directly get into the parts that we have over here. In this chapter, we basically have four things. We have X-ray. So let me show you from the PDF. We have the X-ray, the very stuffs that we have to discuss about X-ray, about what is the underlying principle and producing it, focusing it, using it, getting the information out of it. Then we're going to learn how to use the X-ray in a three-dimensional manner. So that's basically CT scan or computed tomography. That's the full name for CT scan, computed tomography. And then these are two things. And then the third thing that we have is the piezoelectric crystal based upon the ultrasonic ultrasound scanning, which is pretty important for human beings and for a lot of other purposes as well. So we're going to see some calculations and a mechanism regarding that. And lastly, we have MRI, which is magnetic resonance imaging. Magnetic resonance imaging. So this is just the last part of it. The good thing about the medical imaging chapter or the remote sensing chapter is that we have very few mathematical calculation in this thing. I mean, we have some mathematical calculation. Actually, I said it wrong. Forget about that. We have some significant amount of mathematical calculation over here, but additional to those mathematical calculation, we have some pretty high marked descriptive, repetitive kind of descriptive questions which pop up from this chapter. So this question, the marks of this question can vary from 4 to 8, one single question. For example, on the large question that typically goes up is that describe the procedures or the underlying principles for the MRI scanning to work. So you basically have to say everything. If it's an 8-mark question, you have to give 8 individually exclusive information about MRI, about how this works and how the information achieved can be processed to infer data or information about the patient that you are making to undergo that scan. Equally applicable for other things, underlying the describe and explain, or basically discuss the underlying principle between CT scanning or X-ray or ultrasound scanning, and the mark can range from 4 all the way up to 8. So depending upon how much mark do you have to choose your points properly. Cool part, or the advantageous part for this type of large question is that these questions are repetitive, and they are pretty much, one of these questions pretty much pop up every year in every variant of the question paper. So if you can manage to learn these things with, of course, with appropriate understanding. I'm not asking you to memorize them without making sense of them. You should definitely understand what is happening and be able to write them in a logical sequence so that it actually scores you the mark. Because these questions are repetitive, so you know that these kind of questions can show up, and if you have a good preparation for these questions, scoring those marks can prove to be pretty easy. That's point one. The second point is that if these kind of questions don't show up, usually you only have to do a whole amount of math from these chapters. I mean, these typical type of descriptive questions are basically what the theoretical questions are in this chapter of medical imaging. So if they don't give these questions, which is actually quite rare, at least one of these questions do show up. In those cases, you only have to do the math, which makes this the questions from this chapter extremely rewarding, in my opinion, if you know how the math works, for which I'm gonna help and I'm gonna describe and explain how the maths work. Like other chapters, is just a bunch of theory formula, and knowing where to use those formula appropriately is what you have to do. So if we jump in right away, let's do that. Yeah, so this first paragraph that I have crossed out because the CA people decided that you don't need to know this thing anymore. I'm just going to tell you what is included in this paragraph. You can read it up in your own time later on. It basically says that diagnosis can be done in two primary ways. We can do evasive diagnosis, or we can do non-evasive diagnosis. Evasive diagnosis is, let's say I have a tumor in my stomach. So one way to diagnose that problem, that what kind of a trouble that or what state or condition that tumor would be to open up my belly, cut up my stomach, and have a look to see that where that tumor is. That's evasive process of diagnosis. And non-invasive process of diagnosis would be an X-ray or an ultrasound scanning. In my opinion, halfway of evasive and non-evasive process of diagnosis would be an endoscopy, because you actually have to disturb the patient quite a lot for them to go undergo endoscopy. You have to put actually a huge tube that is gonna feed you the video information that's gonna be put into their stomach. So it's not very nice experience. So it's sort of evasive. You actually go into the patient's body to gather information. But then again, you don't essentially damage them. You don't actually cut them open or anything. I mean, once you pull out that video channel fiber optic tube, you're basically done. So in my opinion, it's a halfway thing. So the key idea that I would like you to understand, which is in this crossed out paragraph, is that we have evasive procedure, which means that we're gonna physically get into the patient's body to gather information about their body, or we can have non-invasive procedures in which we scan the patient's body without physically cutting them or physically harming them in any way. So this chapter or this segment of the discussion is all about non-invasive diagnosis. So what are the things that we're going to learn? The first thing that we're going to do is X-ray. So first thing that we have, candidates should be able to explain the principles of the production of X-rays by electron bombardment of a metal target. Bombardment essentially means to shoot something at a very high speed at a very high rate. So basically shooting bullets or stuff like that. So how does this lead up to produce an X-ray? So the basic structure for an X-ray device, a very simplified diagram for an X-ray device can look like this. This is a evacuative chamber where we don't have any gas pressure or very, very, very low atmospheric pressure. We have an electron gun over here. This is the heated cathode filament, which is in this case heated up by this AC supply. And electrons will be produced over here by ionization energy. Then we have connected a high voltage DC source across the two sides. So this is our cathode. And over here we have a fixed piece of metal. Currently, I'm starting to describe this as a fixed piece of metal. There can be some changes brought about to this metal piece upon requirement. So we're going to talk about those changes step by step. For the time being, consider this as a fixed metal plate, metal cylindrical or fixed metal target. And it is connected with a very high voltage DC supply, so that there is a very strong electric field over here. Whenever this cathode produces the free electrons by thermionic emission, the electrons are accelerated through this electric field and they hit this cooled metal anode. Why does it have to be cooled? I'm going to get into that as well. It really has to be cooled, otherwise there'll be significant trouble. And the electrons are going to hit over here. And this heating is essentially what we define as the bombardment. This bombardment will result in X-ray. So what kind of X-rays are we expecting and what can these things do? Once again, I would like to remind you that for most part of this discussion, I'm going to tell you what happens, not why happens. So I'm going to be telling you mostly describing the process, that this is going to happen and after this is going to happen. For most parts, I'm not going to tell you why this happens. So what is the physics, underlying reason, physics reason that this happens in that way. So I'm not going to tell you that, because you will be having these questions. For those of you who actually think about these lectures and actually try to pick as most as you can, you will have those questions. But I'm trying to give a basic disclaimer at the beginning that for most parts, for many of the parts, the why part is not covered in your syllabus, and I will not be covering that. But if you're really interested to find this out, I can guide you to, or redirect you to the necessary study materials from where you can find these stuffs, which is not warranted for your syllabus material. But if you're interested, I can help you to find those. So that can be arranged. The first thing is that you have to, let's have a look at this graph, that on the y-axis we have intensity, on the x-axis we have wavelength. Now try to understand the significance of these two axes. Intensity in this case mean that exactly how much energy per second per meter square, energy per second per meter square, or joule per second per meter square, you're gonna have out of this target area, which is this small rectangle. It's not a hole, it's just a representation of a small rectangle, that this is the place where we are gonna have the X-rays produced out of this heating region. Why only this much? Why not the whole thing, or why not the entire part? We're gonna talk about that in a bit. We have some closing mechanism like this, which limits the region where the incoming electrons will hit. So the purpose of that door mechanism will be discussed later as well. But important for you to understand that whenever the electrons are going to come around, actually, let me just take this into double-sided so that it will be easier for us to see maybe both the images at the same time. I think that works a bit better. AC টা চালাও, fan off করো, প্রচুর শব্দ করে। আমার দিকে আসো, বলুন, just a second. All right. Sorry about the gap. So what is happening over here? Intensity in this case mean that how much energy of how much power are we gonna receive for a specific wavelength of X-ray. So the first thing that I would like you to understand, that the range of wavelength that we have over here, this entire range of wavelength of photons / electromagnetic waves, you can take it either way, wave or particle, we're gonna receive these photons of extra photons by this bombardment. Simply put, we're gonna hit these electrons over here. By some mechanism, these electrons are going to produce the extra photons. And for reasons which I'm about to discuss right now, we're gonna have a huge variation of the output of the photons. So what this graph essentially tells us, that the distribution of intensity versus wavelength, it has a very sharp cutoff on the y-axis. Sharp cutoff on the y-axis means it has an x-axis intercept. I'm gonna AC it on call. It has an x-axis intercept. This means this is the smallest wavelength of X-ray photon that you could possibly achieve for a certain setup of this device. Certain setup means for a specific operating temperature of the filament, and also for a specific amount of DC voltage that is applied across the cathode and the anode. So for one set of these operating conditions, you are gonna get a sharp cutoff of this graph on the x-axis, which means this is the smallest wavelength of the X-ray photon that you could possibly get. Smallest wavelength would essentially mean highest frequency. If you consider E equals to HF, this means the photon or the photons which actually come out at this wavelength has the highest frequency photons, and they also represent the most energetic photons possible to achieve from one given set of operating conditions. Highest energetic photons. This is the keyword that I want you to get in your heads. This sharp cutoff represents the highest energetic photons. Now, interesting for you to see that we are having a sharp cutoff means what? That the number of these photons or the intensity of the X-ray energy that we're going to receive at the supplied by those photons, which has the highest amount of energy, will be very small. I'll tell you again. Each photon has a large amount of energy, but how many of those photons are you gonna get together? This product, that amount of energy of one photon multiplied by number of those photons available from the X-ray device. If you do this two multiplication, you basically get the intensity. Intensity is basically the joule per second per meter square, which means how much joule of energy per second per meter square is available at a certain wavelength. So this intensity basically is a large parameter for how many photons of that wavelengths are coming out from that source. If you have a high intensity, this essentially means that there will be a very large number of photons emitted at that wavelength. There will be a large number of photons emitted at that wavelength, which will give rise to a larger product of energy of the photon multiplied by the number of the photons, which is a pretty big number, which means total amount of energy available at that specific wavelength is going to be pretty large. So intensity versus wavelength, it's not essentially concrete because there are two factors involved: the energy of the one photon and also the number of photons coming out at that wavelength. Both of these factors actually attribute to this thing. It makes it easier for you to comprehend the information on the graph. If you try to think of it in terms of the number of photons, is mostly the factor which the intensity is dealing with. So what I'm trying to tell you is, for places where you have a much higher intensity, these things essentially represent a much higher number of photons. Places where you see a much lower intensity usually represent a much smaller number of photons. It's sort of like a standard deviation curve or normal distribution curve. If for those who have statistics, you know what I'm talking about. I'm not very good at statistics, so that's why I'm using both of these two graphs in a single sentence with OR. But I know to some extent that they shouldn't be used with an OR situation, but I am using it anyway. So the idea is that if you have more of these things, you have more energy available in that wavelength. So you have that part available in the much higher level on the intensity axis. So what this part essentially shows us that as the wavelength, observed wavelength of the X-ray beam that is going to be coming out through this X-ray window, as the observed wavelength will be increased, which means as we are going to slowly observe less and less energetic photon. So first thing first, have a look. This graph has a smooth curve behavior, except for there are some spikes. I'm going to cover the spikes last. There are core three properties that we have to understand for this graph. First property, there is a sharp cutoff. Second property, there is a smooth distribution of intensity for the wavelengths. Smooth distribution, because there's a continuous distribution of the intensity, which means we are going to have X-ray photons at pretty much all the wavelengths. We're not going to miss out any of the wavelength value, because this graph is not essentially becoming zero and eventually spiking up at any point. We're having a continuous distribution, which means there is no wavelength of the observed X-ray behavior or X-ray spectrum that we are missing out. We have some photon of every wavelength, but for some specific wavelength, we have a pretty large amount of intensity. For some wavelengths, we have a pretty small amount of intensity, but we have X-ray photons available for all the intensities. That is the second property, that there is a continuous distribution of intensity for all the wavelengths. Second property. The third property that we have to be able to explain is that why there are certain spikes in specific locations on these curves. So why there are certain spikes? what is the, I mean, why should there be some spikes? So once again, 3 properties. Why there is a cutoff on the x-axis. Number 2, why there is a continuous distribution of wavelengths for all the wavelengths, and why there are certain spikes. This behavior is explained by means of some very minute distribution of the energy of the electron that comes by. So I'm going to put this into some perspective to the best capability that I understand. So I'm going to try to transfer this idea. Have a look. Let's say sorry, I was about to take it, I did not. My bad. So let's try and understand how this is going to work out. So one thing is that, try to understand, let's say we have the metal filament over here. One electron, figure not drawn to scale, is starting its journey at a pretty high speed. For the sake of argument, let's assume each of these electrons, which would be hitting the metal anode right over here, we have a reason to make this conical shape. The main purpose for having this kind of a conical shape or this angled is so that the electrons would hit over here and the X-ray would be beaming downwards, so that we can take out the X-ray through a window in right over here. Because if we did have a cylindrical cross section, I mean, the electrons would hit over here and practically it would be bounced back in the same direction, so it would not essentially be very easy to capture the X-ray beam. So basically what we do, we set up this whole apparatus setup, put the patient right over here, and under the patient we put the extra plate. Or if we don't have, extra plates were actually used in old cases. Directly extra plates were used in older machines. For new machines, we place a sensor, CMOS sensor, which actually captures the extra photons in terms of intensity of bright and dark shadow. You know how things work. I mean, X-rays have more penetrating capability for flesh and blood and skin, but less penetrating power for bones. So that variation of absorption gives us a different variation level of shade of dark color. So the less the penetration, the white it is, and vice versa. So in some cases we have those CMOS sensors, which artificially later on prints out X-ray film in a plastic. So other than for modern X-ray devices, we don't actually place a single X-ray plate behind it. We rather scan it through some digital process and we store this in the digital data. And in any case, we can make multiple copies of, like a photostat machine, we can make multiple copies of the X-ray report, and we can have that. That's just a different way of getting this part. But what we need to understand that we put the patient over here. Behind the patient, we put the detector. In the detector could be a digital detector, CMOS sensors, or it could be a photographic plate directly, which is a basic old version of a sensor. However, the point that I'm trying to make that whenever, let's say for the sake of argument, all of those electrons which will be released, Shubho, you raised your hand, I saw it a bit earlier. I'll give you floor, but let me just finish what I'm trying to explain. I believe many of your questions might get answered in between, so I'll give you floor in due time. What you going to say?
Yes, sir.
Achha. So let's assume, for the sake of easy understanding, that all the electrons which will be released from this metal filament cathode, they will be hitting our anode at the same kinetic energy. Why are we assuming this? For the sake of simplicity. I mean, and also, what is the underlying principle for which we can assume this? If you think that we have connected this to a kilovolt supply or maybe a megavolt supply, depending upon how much energy you want to supply this with, this is the positive and this is the negative end. This has a certain amount of voltage. Let's assume this has a voltage of, let's say, V, whatever that number is. And the energy of an electron is E. So the kinetic energy of the electron would be given by a charge of electron multiplied by the voltage of this thing. And K can be given as half mv square. Or I don't actually write out half mv square, but what you can see, understand that all the electrons will be released from the thermionic emission from the cathode filament. They will all have the same charge because each electron is made up with the same amount of charge. And as long as we are accelerating them by the same amount of DC voltage, they will all be accelerated through the same amount of electric fields, which means equal amount of work will be done on each of the electrons. As a result, as these things will actually hit this cathode, there will be equal amount of work done. You might wonder, well, there is an angle over here, so all these electrons are not going to cover the same amount of direction. So shouldn't there be a difference of the energy? The answer is a solid no. I'll tell you why. This is what's going to happen. The electric field that we're going to have in this place are not going to be essentially horizontal. These electric field lines are going to look something like this, because field lines always come out of the surface perpendicular and get into the surface perpendicular. The potential difference from this part of the coil to this part of the anode is V. The potential difference from this part of the coil to this part of the anode is also V. You just have the lower electrons would have to cover a longer distance under a weaker force, where the upper electrons would have to cover a shorter distance under a stronger force. So practically, the product of force into distance, or in other words, charge into voltage, would be equal for both of them. Bottom line, they would all have the same amount of kinetic energy as they will hit this metal anode. So first thing that I'm establishing over here, each electron comes in with the same amount of kinetic energy. Let's assume the value of this kinetic energy is 20 joule. I'm just picking up a random number, which is not proportional or not even realistic. I could have taken 1000 as well, just to make discussion. This 20 joule of energy can have a lot of different fates. So the first thing that first thing that I'm going to discuss is that it is possible. Not before I go into it is possible. The electrons are going to come in with 20 joule of energy. Each of the electrons are bringing 20 joule of energy to the metal anode, and as they will hit over here, they're going to decelerate. It is this deceleration that will cause these electrons or some other electrons. I'll tell you where these other electrons are coming from. It will cause this deceleration of this particle to give up a portion of their energy. This deceleration of the electrons, rapid deceleration, sudden deceleration as they hit into the metal target, will cause them to release some energy, and that energy release is basically what the X-ray photon is. Now, why do we have a range of these X-ray photons? Because there are multiple things can happen. For very few, like extremely few number of electrons, it is possible that one of these electrons comes in and hit the metal anode, and by only one collision, exclusively by one single collision, it loses all of its energy in a single collision. If you wonder what does a single collision means, that it comes in, the incoming electron comes in, hits one of the surface atom of the metal target, and immediately decelerated to zero. As a result, it will give up all of its energy in a single deceleration process. There will not be any steps. There will not be any breakdowns of this 20 joule of energy. All energy given out as a single photon. That's when this entire 20 joule of energy would be converted into a single photon, in which case we can write this much equals to HF. This will give you the highest frequency possible for this setup of the of your equipment, where each electron could bring 20 joule of energy. And this highest frequency, I can write F max, essentially gives you the minimum lambda. And that is the reason why we have a sharp cutoff at this point. This sharp cutoff of a graph at this point means it is only possible for those electrons exclusively which electrons had their entire kinetic energy converted into one X-ray photon by a single deceleration. There was no breakdown. The probability for this to happen is very low. As you can see in the intensity graph, that the number of electrons which actually undergo this highest photon energy production is really close to zero. I mean, it's very few. I mean, it's really scarce, but it's not absent. So, bottom line, the first observation, there is a sharp cutoff on the x-axis. Why? It is possible for X-ray photon released when the incoming electrons from the cathode decelerates completely by a single collision and gives up their entire kinetic energy as a single X-ray photon, which has the highest amount of possible energy, leading to a smallest wavelength of the electromagnetic wave or X-ray wave. So that's why we have this sharp cutoff, number one. The second thing that we can have, this is scenario number one. Let me write number two over here, maybe number two somewhere else. The second thing that can happen is that electrons can come in, and as they will hit the metal target, they'll be decelerated in stages. If you wonder why stages, try to think about it. A metal structure, if you even consider a pure metal structure, a metal structure is actually layers of metal atoms, and atoms are mostly empty spaces, which means as the incoming electron will hit the metal target, it is quite likely it will not be decelerated completely by a single hit. It will hit the first atom. Now, hitting an atom of the metal target, I mean, hitting an atom right over here, let's say I'm gonna label this atom as maybe green. It's a bit thin. So let's say this atom is green, figure not drawn to scale, obviously. So this electron is coming and hitting this atom. Now, what do you understand by hitting an atom? Is the atom like a bowling ball? Is it a solid object? No, atom is mostly empty space. By hitting an atom, we mean that this high-speed electron which is coming about is gonna hit some of the electron of that metal atom. You have an electron coming in, about to enter into an atom, and about to hit something in the atom, and that hit is most likely to happen with one of the surrounding electrons. If you wonder why not the nucleus, because nucleus is very small. Atom is mostly empty space. Atom is mostly empty space. So the collisions can happen with some of the outer shell layer electrons. So each of those collisions is gonna cause this incoming electron to lose a portion of their energy. So let's say if it so happens that this electron is coming about and it makes two collisions as it is passing to the first atom. Then as it goes into the second atom, it doesn't make any collision. As it goes into the third atom, maybe it makes 2 or 3 more collisions. Maybe it's gonna have a random number of collisions with random number of shell electrons of the metal target. Each of those electrons would take out different amount of energies from the 20 joule energy that this electron was bringing about. As a result, each of those small collisions is gonna give you smaller value of photons. Whenever the electron will be decelerated by a small amount, that reduction of speed will give rise to a production of an extra photon. So every individual deceleration gives rise to one individual extra photon, as long as all of this 20 joule is not converted into extra photons. So this is essentially why we have in this we have in this curve a continuous distribution of intensity over wavelength. It means that whenever we are gonna shoot, we're gonna bombard, or we're gonna shower, or we're gonna brush fire the metal anode with the high-speed electrons coming in from the cathode, it is possible that, or it is more possible, or it is more likely that these electrons, incoming electrons, are not gonna be decelerated by a single step. Most of them will undergo multiple stages of deceleration, and each of these deceleration is gonna produce one individual extra photon. And the energy of this extra photon could be of any value, depending upon how much deceleration that incoming electron was experiencing. These individual random values of deceleration for the incoming electrons give rise to these specific continuous distribution of intensity over wavelength. It means that we are going to have all the possible wavelength for extra photons. Depending upon all the random values of deceleration, these incoming electrons are going to have. We are still talking about the energy given out or photon produced from the incoming electrons. We still haven't talked about what is going to be produced from the metal target atom. Both number 1 and number 2, these two observations are described or explained using the deceleration of the incoming electron, which was accelerated through that electric field, as a result, which had some energy. And if the whole energy converts into a single photon, you have the highest energetic photon or smallest wavelength, explains the cutoff right over here. Sorry, explains the cutoff right over here. Or number 2, because the electrons, most of the electrons are going to have random deceleration values as they hit the metal target and enters into this place, because atom is mostly empty space. Each of those individual deceleration of the incoming electron will give rise to an individual single extra photon, which can have any values. As a result, we can have a lot of individual different extra photons. That's why we have a continuous distribution of wavelength, which means extra photons will be available at all the possible wavelengths, which are definitely higher than this smallest wavelength, because this is the maximum energetic photon you could get, which means you cannot get a photon more energetic than this. So what I'm trying to mean is that if the total amount of energy each of these photons is bringing about is 20 joule, your fractional value of photons can be such that you will have values smaller than 20. You can have 10 plus 10, you can have 12 plus 8, you can have 2 plus 2 plus 2 plus 2 plus 1 plus 0.5 plus. You can have a lot of things which will add up to the 20 joule of energy of one incoming electron, but you can never get a value that is more than 20 joule. If you wonder why, is it not possible that one incoming electron can produce a photon of more than 20 joule? The answer is a solid no. Because, like I said, important information. Each individual deceleration of the incoming electron produces one extra photon. Important information. Keep this in your mind. Each individual deceleration of the incoming electron produces one extra photon. So every single time it will be decelerated by a little value, it will produce an extra photon of that amount of energy. So you cannot decelerate it to a value such that it will be losing more than 20 joule, because it didn't have more than 20 joule to begin with. So it will always produce smaller energetic photons. That's why you have smaller wavelength, we have bigger wavelength, because E equals to HF. So that's point number 2. Point number 3 is about these spikes. Why do we have these spikes? Well, first understand the physical significance as the graph would dictate about the property of the spike. Try to understand. These spikes represent what? These spikes represent that for some very specific wavelength, there'll be some really high intensity of that wavelength, which means at this specific wavelength of extra photon, we're going to have a really large number of photons. For example, what I'm trying to mean, maybe at this photon velocity, I might as well steal this picture from here so that I can draw upon it. Oops. Okay. So what I'm trying to mean is that, let's say at this wavelength value, if I pull this down all the way up over here, let's say at this wavelength value, we might be having, let's say, 2 million photons produced per second. Whenever we have a large higher intensity over here, which is not very different in terms of wavelength, but we have a very large increase in intensity, you might as well understand that at this wavelength value, let me draw that with red maybe, at this wavelength value where we have the spike, the number of photons released per second might as well be 3 million. So you have a sudden rise in the number of photons released. So what is actually happening? Why do we have so many electrons, so many extra photons available at a very specific frequency, which is giving us a spike? These spikes are related to the energy shell values of the metal target. These spikes are related to the energy shell values of the metal target. Here comes the discussion about the metal target atoms. এতক্ষণ পর্যন্ত আমরা incoming electron deceleration দুটা property আলাপ করছি. Now we're talking about what's going to be happening in the metal target atoms. So what I need you to understand that whenever the electrons are going to come up over here and hit these metal atoms over here, like you should remember from the discussion of the quantum physics for the hydrogen atoms jumping procedure, you should remember that we had a thing called the emission spectra, and we had another thing called the absorption spectra. The idea of absorption spectra was that electrons would essentially prefer to absorb a certain amount of energy, which is convenient for them to absorb so that they could make their preferable jump to a higher shell. All the other energies that they are provided, they will not even touch it. If they prefer to take an amount of energy that, let's say, that is 7.3 joule to make a jump from their existing shell to a higher shell, even if you feed them all different type of energies more less than of 7.3 joule, they'll not even touch it. They'll exclusively, preferentially absorb 7.3 joule of photons to make that jump and eventually convert this into something else. That's the whole idea of absorption spectra, that atoms would absorb a very specific type of energy if we allow them to choose. And equally applicable for the case of the flame test or for the emission spectra, that if we heat up a certain element to a very high temperature, we are going to get a very specific frequency of light, because the electrons are going to jump to a higher level and initially they're going to come back from that level, which is going to happen more frequently than others, giving rise to a specific color of that element. Like for sodium, we have golden yellow. For potassium, we have lilac. Calcium has brick red, blah, blah, blah. You know these stuffs. So important part is that every metal atom has a preferred value of jump for their upper level. And as they will come back from that level to the original level, they will emit that photon. Now, because this metal target is made up of a lot of those atoms, and these atoms will be energized from the energy of the incoming electrons. So now we are talking about to the second part, that in this process what's going to happen? Energetic electrons are coming by with 20 joule. Let's say these metal target has preferred energy values of jump, which are marked at, let's say, 4 joule. it appreciates 12 joule, and then it also appreciates 17.5 joule. These are the three defined energy values that these metal targets would appreciate to make their preferable value of jumps. I mean, these are the energy values that matches their energy gaps, which means most of the electrons of these metal targets would either prefer to make this jump or this jump or this jump. So they will be absorbing energies from this 20 joule of electron preferentially out of this thing. For example, let's say first an electron comes in and hits one of this electron over here, and it is coming with the whole 20 joule. So this electron can choose either to absorb 4 joule, this electron can choose either to absorb 12 joule, this electron can choose either to absorb 17. It could choose any of these values. What it's going to choose is something based upon the quantum mechanics, which I don't know, didn't study about it, that what is going to happen exactly. But it is going to choose any of these because it has a supply of 20 joule for the first collision. But if it, let's say, if this first collision absorbs 12 joule, then this incoming electron, as it's going to go further into the metal target, is going to have 8 joule left. It means the next subsequent possible jump it can deliver is only 4 joule. It can no longer make 17.5 joule, which means 12 joules and 4 joules are going to appear in pairs, and they're going to be more common compared to 17.5 joules. Because if you have a 12 joule absorption, there is a subsequent possibility of 4 joule absorption and release as well. Or vice versa, if you have a 4 joule absorption to begin with, you can have a subsequent 12 joule absorption in the second stage. But if you have a 17.5 joule of energy absorption, you cannot have 4 joule or 12 joule, any of those, which means 4 joule and 12 joule will appear as pair. It's possible for them to appear as pair. It doesn't have to be in pair. I'm saying it is possible for them to appear to be in pair, whereas 17.5 joule will only happen individually. So it's a question of which is going to happen more, which is going to happen less. That part I'm not discussing with you. Get this information straight. I don't know this information that which one is going to happen more, which is going to happen less, but it can only happen exclusively at these values. And because the metal target is more prone, is more willing, is more accepting towards accepting these exclusive values of energies from the incoming delivered energy from the incoming electron, they're going to absorb those energies, goes up to the higher energy shell, and immediately come back to the original shell, releasing the photon of that much value. This happening of the or extra photons released of these exclusive energy values are going to be more in number, is going to happen more often compared to the individual energy released by all the incoming electrons. So incoming electrons gula tomar bari খেয়ে খেয়ে যতটুকু ডিসিলেট করতে করতে যতগুলা এনার্জি ইন্টেন্সিটি অফ যতগুলা ফোটন রিলিজ করতে পারবে, because their release photon values would be distributed over a large set of wavelengths. They are not considered at a fixed value. Compared to that, these metal target values, compared to that, the metal target electrons would prefer to give out extra photons at some very specific value of energies. Specific value of energy means E is constant. E means E equals to HF F constant. F constant means lambda constant. Ultimately, that means that for a very specific choice of metal, we're going to have certain spikes. If we change that metal target, we're going to have spikes at different location. You're going to have you're going to have these spikes in certain locations for sodium. If you have this thing as sodium, if you have pure iron, you're going to have other places. If you have magnesium, you're going to have other places. But we can change the location of these spikes by changing the choice of this cathode metal ion. And that is a very important factor for us to choose as for where do we want to use this X-ray. For example, if you want to use an X-ray to scan inside a person's skull, where we have 2 layers of bone, but you still want to do some extra for whatever reason. It's not a very good idea to attempt to X-ray inside a skull. But if you want to do that for whatever reason, then we would require a very high penetrating power of X-ray. So you would essentially expect or want that these spikes should be on the closer to the lower wavelength, because lower wavelength means that you have more energetic photons of high intensity. So you can have more penetrating power. Then again, if you want to scan inside, if you want to scan inside an airport, let's say you want to look into people's baggage, you don't need that much penetrating power because baggages are not supposed to be made up with metals or bones. You can have only cardboards and other stuff. And whenever you are getting blocked, you can make the person open their baggage, and you can either get a blast out of it or you can get some contrabands out of it. Depends upon your luck. But my point being that for cases where you don't need that much penetration power, you'd expect these spikes to be available on the more closer on the higher wavelength side, because higher wavelength would mean smaller energy. So you can choose what kind of purpose you're going to use your X-ray for, and depending upon that, you can essentially choose your cathode metal anode, and that can give you these spikes in different locations based upon what you're going to do. To wrap up, I'll give the whole thing in a very small discussion, last one, and then I'm going to start taking questions. This graph, intensity versus wavelength, has three properties. First property, there is a sharp cutoff on the wavelength axis. This is possible because when all the kinetic energy of the incoming electron is converted into a single X-ray photon by a single deceleration, when it hits the metal anode, it produces X-ray photons of the highest frequency and of the lowest, smallest wavelength. This is represented as the cutoff of the wavelength axis. We cannot have X-ray photons more energetic than this value, or we cannot have X-ray photons of smaller wavelength than this value from that setup of the X-ray tube. Observation 1, explanation, done. Observation 2, there is a continuous distribution of intensity over the wavelength axis. Explanation, the incoming electrons lose their energy as they hit the target metal anode atoms, and for each of the individual deceleration, they give up one photon. Now they can have multiple decelerations depending upon where they are hitting on the metal target, and because atom is mostly empty space, they can have a lot of individual small decelerations. Each of these small decelerations gives up one photon. These photons can be of any value, and depending upon the energy range, this, you can see that this graph, it looks like a normal distribution curve, which means that there is some correlation with that. I'm not getting into that, but there is actually a correlation with that, which means we can have X-ray photons available at all the possible wavelengths, but there is a distribution of energy. But it is possible for us to have X-ray photons of all possible wavelengths, because incoming electrons can have all possible values of decelerations, resulting in a lot of range of X-ray photon wavelengths. Observation 2, done. Observation 3, there are certain spikes in this graph. Why? Explanation, whenever the energy, kinetic energy of the incoming electron is delivered to a metal target atom's electron, metal target anode's electron, atom's electron, and that target electron, not the incoming electron, target electron takes a preferred jump depending upon its energy shell difference, then, and it comes back to its original shell, it gives up a very specific value of X-ray photon. These jumps happen more frequently compared to other type of X-ray emission. That's what gives us a much higher intensity or more emission per second of energy at that wavelength value. In simpler terms, these spikes exist because of the energy shell difference of the metal target atom's electron shell values. এই হচ্ছে total explanation. Last thing that I'm going to wrap up, then I'm going to take questions. সেটা হচ্ছে, all in this process, all the 20 joule of this energy, you can see over here that I've written 20 joule of energy. This in no case, I mean, except for the case number 1 where we have the sharp cutoff, except for this case, a significant portion of this energy of one electron is actually absorbed in this metal target as heat. Because whenever this electron actually make a collision over here, they make vibration. Vibration essentially transcends into heat energy into the metal target, which means this metal target is going to become heated in a very short time. We have to have a proper cooling system available for this metal target if it is supposed to work normally. There are multiple things that we can do that is covered in your syllabus. One thing that we can do is that we can have this thing cooled by either some liquid flowing over here, or we can have some airflow with black fins connected, something like the CPU cooler or the processor cooler heatsink that we have in our computers. Many of you might have seen, or behind the air conditioned radiator, they have also these fins across the pipes. So we can have that kind of cooling system. Another thing we can do is that along with the cooling system, we can also do one thing. Other than having this thing in this conical shape, maybe, let me just show you a different shape so that it's easier for you to understand. Let's say this is the coil, from where we are producing the electrons. Electrons are going to shoot in this direction, and this is our tube of the X-ray tube. We're going to allow the X-ray come out through here. So I'm going to just make a little bit of gap over here. It's essentially evacuated, so this gap is not basically open space. Just trying to show you where the X-ray beam is going to be out, and the patient is going to be over here. Let's say this is the patient. This is the belly of the patient, head, no neck whatsoever, and small legs. And also, we can also have, other than having the cooling system, we can have an angled metal target which has a cylindrical opening. So let's say this is a cylindrical opening, a cylindrical face, and this beam is controlled with those metal doors that which I showed you a bit earlier. Let's say the doors allows the beam to hit right up to this space. So right up over here. This is the amount of location where it's going to hit. So what we can do that we can continuously rotate this target so that this beam of the incoming X-ray, incoming electrons will not always hit in the same location. We can distribute that hitting location over a larger circular or a cylindrical region so that the effect of the heat is distributed and it is easier to dissipate that heat energy. So that's also a very required operation for the device to be long lasting. That's pretty much it what is said over here for a pretty big part. I'll take questions. Shoot.
Sir.
Yes.
Sir, intensity টা এখানে কিভাবে ক্যালকুলেট করতে হবে জানেন?
Energy of one photon multiplied by number of photons released per second.
মানে বেসিক্যালি এখানে ইন্টেন্সিটি বলতে তো আমরা বুঝছি যে
energy per second,
total energy released by the per second
per meter square.
আর স্যার এখানে যে আমাদেরকে বলা হলো যে হচ্ছে there are some photons which are like there are some electrons which একটা single deceleration এ হচ্ছে পাস করতেছে.
Very few of them undergo this, but yes, it is possible.
তো স্যার ওগুলা কি পুরা মানে কুলড মেটাল অ্যানোডের ভিতর তো পুরা স্যার হচ্ছে মানে স্ট্রেট চলে পাস করে চলে যাচ্ছে জাস্ট একবার কলিশন করে
একটা কলিশন করে সে ডিসেলারেট করে সে স্টপ হয়ে যাচ্ছে পাস করে গেলে তো সে কাইনেটিক এনার্জি থাকলোই the electron will come and hit and decelerate to rest immediately by a single collision.
আচ্ছা
and if you wonder that why this electron would not be a problem, because you should see that in this place to operate this thing we have connected this to a high DC supply. It means this is always maintained as at a positive potential, so whatever the electrons come and hit over here they get absorbed to the source automatically, so this thing does not become negatively charged whatsoever. বুঝা গেছে?
জি স্যার.
Beautiful. Anyone? Anything else?
এটা জাস্ট কনফিউশন ছিল যে লাইক যে কন্টিনিউয়াস স্পেকট্রামটা শো করছে these are like because যে ইলেকট্রনটা হিট করছে ওইটার থেকে এনার্জি রিলিজড হয়ে ফোটন রিলিজ হচ্ছে.
Yes, and that is happening because of multiple different intermittent decelerations.
And this is not related to the absorption spectrum. ওটা তো হচ্ছে স্পাইকের জন্য.
No, this is not related to absorption spectrum at all. This is about the continuous distribution is attributed towards atom being mostly an empty space, and it is possible for the incoming electron to decelerate at any random value as it passes through the electron structure or the lattice structure of that metal target.
আচ্ছা একটা জিনিস ছিল যে এই কাট অফ পয়েন্টটাতে why is the intensity zero? Like intensity is the measurement of the energy, right? তো এনার্জি তো 20 কিলোজুল থাকবে. তো
intensity zero মানে হচ্ছে you are not going to have any photon available out of your setup which is going to have an energy of more than 20 joule. The maximum extra photon energy that you could possibly get out of this setup is 20 joule. So ওই 20 joule photoনের জন্য তুমি একটা relevant frequency পাবা, ওই frequencyর জন্য তুমি একটা relevant wavelength পাবা, right? And that is the highest frequency you could possibly achieve out of 20 joule. That is the smallest wavelength you could possibly achieve if you go 20 joule. You cannot get an extra photon at a wavelength lower than that. That's why we have zero on the left of this curve. And that at this point we have this graph getting started means the number of this happening or this amount of large deceleration happening I'm referring to as this is a large distillation because the entire electron is stopped in one single collision. The probability for this to happen is very low. That's why number of photons released with that high amount of of energy is actually very few.
Yes, sir.
Anything else? Anyone? এই গ্রাফটা বুঝা গেছে? এই গ্রাফের উপর থেকে থিওরিটিক্যাল কোশ্চেন হয়। আমি এটা এতখানি সময় নিয়ে বোঝানোর মেইন রিজনটা হচ্ছে সো দ্যাট ইউ ডো নট গেট কনফিউজড অ্যাবাউট দিস।
স্যার যেটা একেবারে স্মুথ শেপ হচ্ছে যে হচ্ছে গ্রাফে, ওটা তো বিকজ অফ দ্য ইন্টারমিটেন্ট কলিশনস, মানে ওটার সঙ্গে রিলেটেড না স্যার?
Yes, small decelerations continuously.
And স্যার আপনি আরেকটা কথা বলছিলেন যে পেয়ারে আসবে, মানে ইট ক্যান বি লাইক 4 and 12, মানে ওই পার্টটা আমি আসলে ঠিকমতো বুঝি নাই।
এটা যেটা বলতেছি সেটা হচ্ছে যে if the this was about the spike values, this values are about the spikes, is that if the preferred jump value for the target metals atoms to go above, they have these energy values in their energy gaps in their shell electrons. এটা এই কথাটা কি বুঝতেছো? shell electron energy gap?
হ্যাঁ স্যার বুঝতে পারছি, মানে সেকেন্ড এনার্জি শেল আর থার্ড এনার্জি শেলের ভিতরে
হ্যাঁ
এনার্জি গ্যাপ
এরকম। সো আমি মনে করো যদি ইলেকট্রনের প্রেফার্ড এনার্জি জাম্প লেভেলের রিকোয়ার্ড এনার্জি যদি 4 এবং 12 হয়, একটা ইলেকট্রন ইনকামিং ইলেকট্রন থেকে মনে করো 4 জুল অ্যাবজর্ব হয়ে গেছে, সো তার কাছে এখন 16 জুল বাকি আছে। সো ইট ইজ পসিবল ফর দ্যাট ইলেকট্রন টু মেক অ্যানাদার extra photon released at 12 joule. So it can make 4 joule and 12 joule subsequently from a single incoming electron's energy. So 4 and 12 can happen simultaneously from a single electron. But but on the other hand, if the electron loses 17.5 joule of energy for that amount of collision, then it would only have 3.5 joule left, 2.5 joule left. 2.5 joule cannot give another spike value. 2.5 joule would be somewhere on this curve.
মানে স্যার দুইটা কলিশন হলে সেটার জন্য মানে সাফিশিয়েন্ট এনার্জি থাকতে হবে, লাইক
exactly
সো দ্যাট এনার্জি মানে লেভেলটা ক্রস করতে পারে।
exactly. হ্যাঁ আবিয়াস বলো।
Sir, could you re-explain the first observation of the sharp?
I will. The sharp cutoff on the wavelength axis represent an extra photon or some extra photons released at the smallest wavelength attributed to the highest possible frequency, means highest energetic photon, highest energetic extra photon released out of this process. Possible to happen if the incoming electrons decelerate in a single collision and produces an extra photon with all the kinetic energy they were coming with in only one single photon. No breakdown whatsoever.
So this is just a pretty rare case.
Exactly.
For the sharp.
This will happen very rarely. That's why the intensity is so low at that. Even though the extra photons individual energy is very high, the total intensity that you're going to get at that wavelength is extremely small because the number of times this will happen is very scarce. I would like all of you to read through this paragraph a little bit, this one, and then should I zoom out? Can you read? Because here এই পার্টটুকু একটু পড়ো সবাই, এই পার্টটুকু একটু পড়ো। If you have any question from here, I'll take questions from here. Everyone, এইটুকু একটু পড়ো।
স্যার
বলো।
আপনি যে রিয়ার কেসের কথাটা বললেন যেখানে হচ্ছে একটা কলিশনে এই সব মানে সবগুলো এনার্জি দিয়ে দিচ্ছে 20 জুল, ওখানে তো ওটা অনেক রিয়ার কেস, মানে একটু হলেও তো ওখান থেকে ফোটন বের হবে না, মানে কম হলো, তাহলে ইন্টেন্সিটি কেন জিরো এখানে? একটু হওয়ার কথা না, বা অনেক কম?
যেই ভ্যালু exactly 20 joule is that value where you're going to have the sharp cutoff, which means that exactly 20 joule এর জন্য যে রিলেভেন্ট ওয়েভলেংথ ওইটাতে তোমার গ্রাফটা স্টার্ট হচ্ছে, তার লেফটে আর গ্রাফটা থাকবে না।
এখানে ইন্টারসেপ্ট মানে হওয়ার মানে হইলো কেন, এটা একটু উপর থেকে হয়তো স্টার্ট হতে পারতো, কারণ এখানে তো একটুখানি হইলেও ইন্টেন্সিটি থাকবে, কারণ ফোটন তো একটু হইলেও আছে, মানে কম হইলেও তো আছে।
I'll tell you this. দাঁড়াও, একে দেখাচ্ছি আমি। I get your question. I totally get your question. ধরো এটা হচ্ছে আমাদের এক্সেস, ঠিক আছে? মনে করো 20 জুলের জন্য আমাদের রিলেভেন্ট ফ্রিকোয়েন্সি হচ্ছে লেটস সে রিলেভেন্ট ফ্রিকোয়েন্সি হচ্ছে ধরো 100, এই 100 this is the frequency whatever unit. I'm just giving numbers and let's say for that frequency the relevant wavelength is supposed to be let's say 2. So এটা মনে করো আমাদের wavelength axis whatever unit and let's say this is the value of 2. তার মানে হচ্ছে exactly 2 ভ্যালুতে আমাদের কিছু হলেও ফোটন রিলিজ হবে। This is exactly where the car graph will get start. You're not gonna have before 2. You're gonna have some value at 2. Z2 is the point for the graph to become started, which means you cannot say at 2 the intensity is 0. At 2 the intensity is something slightly larger than 0. This is exactly where the value is getting started. This is the borderline where the incident is beginning. বুঝতে পারছি?
তো স্যার আপনি না মাত্র বললেন যে at 2 the intensity will not be 0, কিন্তু এখন তো ইন্টারসেপ্ট আছে, তাহলে তো 0ই হচ্ছে।
That's my point, that exactly at the starting point, যেটা হচ্ছে exactly starting point, ওইখানে তো আমাদের মানে let's say এই পয়েন্টের আমি যদি exactly এই পয়েন্টের y axis ভ্যালু বলি তোমাকে, exactly এই পয়েন্টের y axis ভ্যালু তুমি কত বলবা? 0 বলবা না?
হ্যাঁ।
But technically speaking it will not be exactly 0, it will be very small. So আমি যদি এই পার্টটুকে মনে করো super highly magnify করি, maybe it is possible that at 2 we're going to have some value at let's say 1.999999999 we're going to have 0, technically speaking.
আচ্ছা, এটাই বলতেছিলাম যে একটু তো থাকবেই।
হ্যাঁ হ্যাঁ, একটু হলেও থাকবে।
আচ্ছা স্যার, থ্যাংক ইউ।
Sure. So this was that, and the next thing that we're going to talk about is that how can we use this X-ray beam that will be available coming out from the X-ray tube to be used for diagnosis. So diagnosis করার জন্য এই X-ray beam কে আমাদেরকে কিভাবে প্রসেস করতে হবে? So this is just raw X-ray beam coming out and we want to use it to do some diagnosis, and এই diagnosis এর প্রসেস কি সেটা এখানে বলে দেওয়া আছে। আমি কয়েকটা বেসিক টার্ম বলতেছি and then you can read through this part and then I can take questions from here. So আবার শুনে যাও। যে কোনো একটা X-ray beam এর দুই সেট প্রপার্টি আছে, একটা হচ্ছে হার্ডনেস আরটা হচ্ছে কই জানি গেল, হারাই ফেলছি, তার ওখানে পড়া লাগবে আমার। হ্যাঁ, ইন্টেন্সিটি। এই যে এখানে দুইটা প্রপার্টি দেওয়া আছে। One of the important property for the X-ray beam is the intensity of the X-ray beam. This is the property of the beam, remember. The X-ray beam that will be released from the X-ray tube can have two properties. One is intensity, the other one is hardness. Intensity of the X-ray beam is determined by the rate of arrival of electrons at the metal target. Intensity basically means energy released per second. So if more electrons are coming over here every second, you'll be having more intensity or more energy released per second. So the intensity of the produced X-ray beam is dependent directly upon the rate of electron arrival. Rate of electron arrival basically means the current that flows through this empty evacuated chamber, or sometimes we can also say that to be tube current, which is mentioned over here. The intensity of X-ray beam is determined by the rate of arrival of electrons at the metal target, that is the tube current. Tube current means total amount of charge over unit time that travels through this gap. The tube current is controlled by the heater current in the cathode. Heater current in the cathode মানে হচ্ছে এই small tube যে current. If you allow more current, the temperature of the thermionic emission would be more. Higher temperature would essentially mean more thermal electrons produced per second, and as a result, you can have more intensity. More intensity essentially means that you are producing X-ray beam with more energy, but not essentially more energetic photons. This is important, because intensity is determined or primarily attributed to the rate of electron hitting the metal target. The second property of the beam is hardness. Hardness is about the penetrating capability of the beam. Penetrating capability of the beam essentially depends upon the individual energy of X-ray photon. that how much energetic is each X-ray photon is, or in other words, you can say that what is the most, or we can say that, or in general terms, I can say that higher energetic photons will have more penetrating power. So if you have your X-ray photons produced at a much lower wavelength or at a much higher frequency of the electromagnetic spectrum, then they will be able to have higher penetrating power. So let's say if you want to use your X-ray beam to determine the quality of a metal block produced in your in a factory, you might as well want to have a really hard X-ray that will have a very strong penetrating power, be able to go through thick materials. And if you want trying to do some weak X-ray, you would appreciate them to have less hardness. Hardness is about the value of the photon, X-ray photon, where the value of energy of each individual X-ray photon. If we want to have higher hardness of an X-ray beam, we need to consist that X-ray beam with higher energetic X-ray photons. Now, try to understand, higher energetic X-ray photons is only possible if you have higher amount of kinetic energy of the incoming electron to begin with. If you want to achieve more energetic X-ray photons, if you want to produce more energetic X-ray photons, you would primarily you would require more energy to be carried in by each individual electron that is gonna hit your metal anode target, which means you have to somehow increase this energy value. Now have a look this equation that we just wrote about, that this kinetic energy value was directly coming from the product of the electron's charge, which is practically a constant. There is no value change over here, multiplied by the voltage that by which we are actually making this acceleration possible. Which means if we want to increase the individual electron's energy, we have to increase this voltage value. So vice versa, if we have a higher accelerating voltage, we have a higher individual kinetic energy for the incoming electrons, collisions can give rise to higher energetic photons. So which means hardness of an X-ray beam can be controlled by controlling this voltage. Bottom line, intensity of the X-ray beam is controlled by the tube current, or the voltage operating the cathode filament, or the temperature of the cathode filament. Any three of these variables are relevant. Intensity is controlled by any of these three. Hardness of the X-ray beam is controlled by the value of the accelerating voltage. Bigger accelerating voltage means incoming electrons will come with more energy, more kinetic energy, and the deceleration can subsequently produce X-ray photons of higher energy values, giving rise to more penetrating capability for their X-ray beam, hence higher hardness. The next thing that I need you to understand, these are the two properties, intensity and hardness are the two properties of the X-ray beam produced out of the tube. Then the image that we're going to produce out of this X-ray beam after scanning the patient, let's say this is the patient's body, this is a bone, so this is the film or the detector. So we're going to produce an image over here. This image that we're going to produce, the X-ray image that we're going to produce for our diagnosis, that can also have two individual properties. And those two properties are, one of them is called the, what is it called? Sharpness and contrast. You have a look over here. The quality of the shadow picture, the image produced on the photographic plate, depends on its sharpness and contrast. These are the two other properties, but these two properties belong to the X-ray image. So not to mess up these two set of properties. Beam has two properties, intensity and hardness. The X-ray image has two properties, sharpness and contrast. I'll tell you one of them individually. The idea of sharpness is how distinguishable the border of a certain thing is in the picture. For example, if you try to think of a regular thing, if you take an image out of your cell phone, if it is not properly focused, the object that you're trying to take the picture will have a blurred outline. It will be hazy. It means it has less sharpness. You do not want that kind of a picture out of your X-ray image. You want to have a really sharp image so that you can determine any break or any crack in the bone or any other imperfections of your metal production output, whatever that is. So we want a sharp picture. We want the border of the object that we're trying to scan to be properly outlined. That's about sharpness. Point one. Point two, contrast. Contrast is about how distinguishable is multiple areas of black and white image. What I'm trying to say is that let's say if I'm about to take the scan of of a human body, let's say if the thigh of a certain person is scanned, the location where the bone runs should have one type of shadow color compared to the location where the bone is not running. If the person got hit by an iron nail, or if there is a bullet in their thigh, that bullet should give us a very distinguishable shadow color compared to the flesh that is around. If it so happens that the bone, bullet, and the flesh, they all give the similar shadow color, then practically there is no contrast difference, and that basically nullifies the whole purpose of the X-ray imaging. There has to be a proper distinguishable difference between different locations which are different from each other in terms of the depth of the shadow. Places which absorbs more X-ray should be lighter or more whitish. Places which absorb less X-ray, which allows more X-ray to pass through, should be more darker. So different regions of the X-ray image should have proper variation of contrast for it to be a good X-ray image. This is also even more important whenever we have overlapping parts of the bone. For example, whenever a patient is about to take a chest X-ray, you have to think about it. Chest X-ray essentially includes overlapping rib structure. You have the whole backbone in the back, and then you have the ribs coming out from the back of the backbone. They wrap around the cage in front of the thing, and then there is a sternum, which is the cartilage that joins up the rib structures. Which means whenever they're going to take a front or back, a front X-ray, they're going to be overlapping ribs on two parts. So places where the ribs are going to cross into each other, you should have even more absorption of X-ray. So those parts should be even more lighter. Where there is a single rib, that should be a bit more darker. Where there is no ribs whatsoever, the entire flesh or fat tissues or muscles, that should be even more darker. So there should be a distinguishable variation of the black and white color of that image. And also those regions which are supposed to have different colors should be properly outlined, which means the sharpness. These two things together make a good X-ray image. Now, how can we achieve this stuff? So there are multiple different ways. The ways that we're discussing over here are very overly simplified for what is actually done in an X-ray machine, but the principle is basically same. The first thing that you can see in figure 2.3, it shows us that if we have a larger region, if you have a small region of electron shooting, which means the location where the electrons are hitting or the target area of the anode is pretty small, that gives us a very thin partial shadow. These have some name, numbras, umbras, and penumbras, and something under this kind of names, full shadow, partial shadow. You don't have to remember those names. I find them confusing very much. So you can just write these things, partial shadow, full shadow, partial shadow, which works. What they're trying to show you is that whenever the anode target area is small or your source of the X-ray beam is small, then you're gonna have a thin partial shadow, and you're gonna have a full shadow which is pretty large. So what I'm trying to get over here, this part, above this line, you're gonna have an entire exposure of X-ray beam. This part is gonna have zero exposure of X-ray beam, and this part is gonna have a halfway merge of X-ray beam, which means this region where you're gonna have a transition from white to black, this part is gonna be somewhat shady. This partial shadow region will basically outline the possible border of the black object that is over here. So this is not going to be very beautiful because the outline would be actually hazy because it's not a properly focused image. This thing would be even worse if the target area of the anode was even bigger. The bigger the target area of the anode is, or the wider or the vivid the source is, your partial shadow region is going to get even thicker, making the object lose more of its sharpness. The point that they are trying to show us over here is that the smaller the target area on the anode, the better the sharpness is going to be. So if we make the target, if we make the electrons hit a very small region on the metal target, then the image produced on the X-ray film can be achieved to be much more sharper. That's where this metal target thing comes in. This is basically an aluminum or some other metal window. This can be slided into and out of the whole thing. This metal door is actually placed right over here. সেখানে আমি ইমেজটা কপি করে নিই, দাঁড়াও ইমেজটা কপি করে আনি, হোল্ড আপ। Let's say patient koi. Alright, let's say এই হচ্ছে আমাদের এক্সরে বিম, ঠিক আছে? তো এখানে হচ্ছে পেশেন্ট, এই হচ্ছে পেশেন্ট, মাথা এন্ড পা এন্ড হাত এন্ড হেয়ার, লেটস সে তার নিচে হচ্ছে আমাদের এক্সরে প্লেট, ঠিক আছে? সো উই গোনা সি সাম what can I place inside the patient's body? That's weird. Dick bud. No, dick bud. Never mind. Whatever. We're gonna see some random shit from inside the patient's body, which is gonna show over here. Forget about it. So, in this case, gallbladder stone. So, in this case, we are trying to place this mechanism. Which mechanism? In this case, we are trying to place. Actually, let me get this in view. This view. We're trying to place these overlapping metal plates to limit the target area. So which means this has to be placed in the path of the electrons, which means those structures that you just saw are going to be placed somewhere over here. Now I'm showing this as a straight line because this will be actually metal pieces. Just to make sure that it's going to be perfectly straight, I'm going to give a small bit of gap over here. So this will be located here to limit exactly how much part of the anode do we want to eliminate by the incoming electrons, and that can give us a much bigger sharpness. That's one thing. The second thing that is important for us, the second thing that we can do to increase the sharpness is to reduce unnecessary radiation passing through. Now let me tell you what this means. One thing that I need all of you to understand. Our aim is to take an image of the patient's inside without harming or damaging the patient. This is very, very basic. We don't want the patient to undergo any harm just because we want to diagnose this patient. That's the whole point of non-invasive procedure. Now, whenever we'll do an X-ray of a patient, we will make the patient to absorb a significant amount of higher radiation photons into their body, which if the patient did not take the X-ray wouldn't have to go through, which means their body is absorbing significantly higher dosage of energetic radiation. If you ask me, is it possible for the patient to grow some tumor and cancer cell out of this thing? The answer is the possibility is non-zero. They can have some growth of these things. However, we don't want this to happen because we want the patient to be, we want patient's welfare. So what we would appreciate that we don't want the patient to absorb any more of radiation dose than it is absolutely necessary for us to diagnose. So if it is possible for us to somehow achieve a smaller radiation dose to pass through the patient's body, we're going to adopt that mechanism. So we're only going to allow the minimum amount of radiation that the patient has to absorb for us to able to take a good picture. That's it. We will not expose the patient to more than what is minimum required for the diagnosis process. This means that all the X-ray beams that we're going to produce out of this thing, we are not going to allow all the X-ray beam into the patient's body. We're going to allow a small fraction of it in the region that we require. And any part of the X-ray beam that might as well be not necessary / not useful for us for our diagnosis, we're going to cut it off. For example, whenever we'll produce an X-ray beam out of this, if you recall from this figure of the graph, we're going to produce a lot of low wavelength beams. Now, here's the part that I really want you to understand. We do not want to send into a patient's body X-ray beams, which will be by default get absorbed by flesh. If you're trying to take an image of a patient's body, we want to send at least that much energetic beam to the patient's body that will be at least be able to penetrate to the thickest amount of the shell that the person has, so that those extra photons can penetrate through the flesh and come out on the other side, don't get absorbed in the patient's body preferably, and the bones would be absorbing them, but the flesh would not. Which means if we send some photons into the patient's body which are less energetic than that, then they will be by default absorbed in the muscle. Absorbed photons in the muscle doesn't practically give us any practical benefit on the diagnosis side, because that is not seen or visible on the X-ray beam. It is simply increasing the risk for the patient to have towards having a tumor or cancer growth. We don't want that. So what we're going to do, we're going to cut off a significant portion of these higher wavelength X-ray photons or low frequency X-ray photons or less hard X-ray photons which don't have much penetrating capability. We're going to cut these off. They're going to be by default be produced from the anode. We cannot stop their production, but we're not going to let those photons enter into the patient's body. So what we're going to do, we're going to place, after the X-ray beam comes out, or maybe inside the tube.
Did you say higher energy photons?
We're going to allow the higher energy photons to pass through the patient's body, which is going to be differently absorbed by the bone or the flesh.
আচ্ছা, but lower energy যেগুলো সেগুলো আমরা দিতে চাচ্ছি না।
দিতে যাচ্ছি না, exactly.
আচ্ছা,
ঠিক আছে? So we're gonna have to stop those photons entering the patient body. So we have to to achieve this, we place and typically we use a thin aluminum sheet that will gonna absorb up all the low energy photons before it is sent to the patient body. So that barrier could be placed here, that barrier could be placed here, anywhere before the patient's body we can place that barrier. That location is not necessarily specified, yet different machine can have different designs, but there should be a certain barrier which will be responsible to absorb all the low energy photons which will not be required for our diagnosis, but it will simply increase the radiation dose received by the patient. So we're going to cut off those low energy photons, only make the patient to absorb or undergo the penetration of a set of high energetic photons which will be differently absorbed by flesh and bone, or at least those energetic photons which will be absorbed by bones but not at all be absorbed by flesh. If they're going through flesh, they're going to be completely passing through. We are going to allow that amount of energy. So this is also this is essentially this part that I'm discussing to you is not attributed towards the quality of the image. This is attributed to the overall health and safety of the patient who is undergoing through the diagnosis process. This is not attributed towards the diagnosis output. This is attributed towards the patient's welfare. It's very important, so you shouldn't forget about this. Description গুলো আমাদের ওখানে আছে লেখা আছে, আমি আমার মতো করে বুঝাচ্ছি যাতে তোমরা প্রপারলি মনে রাখতে পারো। One more thing that we can achieve, that we can add to get an even better figure is what is shown in this part. This thing is what we call a collimator. A collimator is basically like a wind tunnel, but made up of metal. Do you guys remember what the structure of a wind tunnel? Rectangular or hexagonal honeycomb structure, long. মনে আছে কারো? If for those who don't remember this shape, let me just show you a little bit. Where is the laminar flow making thing? Is that no, that's not it. Is it? Yes, this is it. But I would like you to show a more detailed view. Actually, they are giving us the view wind tunnel inside honeycomb structure. Let me just write it. Honeycomb. Exactly. This is the type of structure that is usually introduced inside inside a wind tunnel, and which is all. And if this thing is made up from metal, this is basically what is called the collimator. So on a second tab, I can try to find out collimator. Collimator. Okay, these are all. Yeah, this is actually a pretty nice representation for what a collimator practically does. What this is showing us that if we are sending a group of light, a group of beam which are at all different angles, and it is a long narrow tube, all the beams which are coming at some angles are they're gonna get hit this inside border of this metal structure, and only those which are coming at some almost in straight lines, almost. I'm using the term almost because there's a gap, so you can always accommodate for some angle. So beams which are coming almost parallel to this gap or with a very negligible amount of amount of angle, only they can come out on the other side, which means these beams which are going to be coming out of the collimator side are going to be practically parallel, practically, not theoretically. They're going to be practically parallel, but entry beams can be somewhat disdirected, not parallel. Why am I telling you this? What is the purpose of this? The purpose of the collimator is to give us a much better image. Let me tell you what is happening. Let's say this is the patient's thigh. Very simple, because you can see there is a huge lump of flesh and there is a small piece of cross-section of a bone. So thigh is a pretty good example for this one. Or it could be anything else. It could be someone's neck as well. For example, this is the whole centrum, the neck bone, and this is the whole thing around them. Pretty fat person, I'd say, a large amount of fat behind their neck, whatever. So point that I'm trying to make is that this is, let's say this is a person's body that we are trying to have a scan. You have to understand that the X-ray beam will be affected. X-ray beam is basically what? It's a photon. And it's an electromagnetic wave. Waves get reflected off hard surfaces. Our body contains a lot of hard ions. In our blood, we have iron. In our blood, we have other heavy metals, and calcium, and we have a little bit of other trace element. I don't know about the macro and micronutrients, but we have heavy metal ions, metal atoms present in our bloodstream, in our skin, in our flesh. We need those. These individual location of atoms, it is possible that the X-ray beam or X-ray photons which are sent to the patient's body, they can reflect it off those individual atoms. So we are talking about super microscopic level. And because of those presence of those atoms, you can see that some of these X-ray beams are apparently bouncing off from random locations in the flesh. You can see one is here, another one is here, another one is here, another is here. Even before hitting the bone, they are getting bouncing off. So what is happening? It is those individual heavy atoms which is causing these microscopic level deflections. If you wonder, is it really significant? The answer is yes, because we are talking about a human bone. So we're talking about a human body, a certain location of human body that can be for like millions of those atoms, because molecular weight is not that high. You don't need much to make a million of, I mean, a very small fraction of a mole give you 1 million of an atom of that element, because Avogadro's number is really, really large. Yeah, exactly. So 6.023 is a pretty large number. So the point that I'm trying to make, this happens quite for a good number of X-ray photons. So even though the incoming X-ray beams are pretty parallel, now we might wonder, how did this beam become parallel in the first place? Well, obviously, to make this beam parallel, or to make sure that these beams are also made parallel as they are coming out of this plate, one important thing is that we can place one collimator first before the patient. So what we're gonna do, let me just show you this. That we can place one set of collimator. Let me draw the collimator with maybe blue. We're gonna place one set of collimator before the patient to make the beam parallel. And we're gonna set one set of collimator after the patient to make sure that all the X-ray beams which got deflected in random directions are not gonna get absorbed over here, because here's a problem that will happen. Let's say if we don't use this collimator after this patient, if you don't use this collimator after this patient, all of these randomly deflected beams are gonna hit somewhere on the X-ray film. So it would mean, so if we allow this to happen, whenever we'll develop this film and you have a look, we'll see that in random places there is a sharp black spot. In random place there is a sharp white missing darkness. So there will be random specks of light in different places of the X-ray plate, which is just because of this kind of deflection. Now you have to understand, we are taking X-ray image entire and we're taking information out of it based upon the difference of contrast. So if some locations look darker than other locations, you have to understand that there is a problem that we are not expecting. So that location needs to be diagnosed more carefully. So every bit of difference of contrast from one location to another location because of maybe even one X-ray photon popping up in random place can mislead us about the diagnosis. We don't want that to happen. To avoid this problem, to avoid getting these X-ray photons reaching to random places on the X-ray film in our diagnosis, we use a collimator over here. The purpose is pretty simple. You can see because of the collimator, all the X-ray photons which are actually diffraction in random angles, they're getting either absorbed on the body of the collimator or they're getting absorbed on the inside of the collimator. And only the beams which are parallel basically come here. So you can see very well that over in this location, we pretty much have an uniform amount of penetration, no amount of penetration, and then once again uniform amount of penetration, giving us a pretty good uniform contrast image, flesh, bone, flesh, with no apparent disturbances or wrong information that we could possibly be misguided by. So that's the purpose of the collimator, which increases the sharpness of the image, which gives us a much better borderline view of the bone that we are trying to get. You might wonder, does this not cost us a significant reduction of contrast? The answer is yes, because we are essentially stopping some of the X-ray photons to actually reach up to our film. We are essentially sacrificing a bit of a contrast, but there are other ways by which we can increase the contrast. One way to increase the contrast for digital X-ray mechanism is just by software, because in the digital X-ray you just take the information by CMOS sensors, and then you can print your X-ray plate at any level of contrast that you want to print, because with software we can print it pretty easily. But back when digital X-ray was not so available, when people only used to directly use the photographic plates, in those cases we used to do one thing, is that when the film was developed, additional developer solution was used, which would increase the effect of contrast. So the developer solution would work in such a way that places which are supposed to be dark would be darkened, places which are supposed to be light would be lightened. So it will enhance the contrast of that photographic plate more than what it would have been exclusively out of the X-ray plate process. So this kind of material can also be, so this is this line that it means that contrast may be improved by backing the photographic film with a fluorescent material. Backing the photographic film with the fluorescent material means if we place a fluorescent material over here, let's say this is the film, we are placing a fluorescent material over here, what's going to happen, that locations where the X-ray beam will reach, those locations are going to light up. So you're going to have more darkening of that region because of the fluorescent light, and locations where you don't having the X-ray beam reaching, in those locations the X-rays are not making any penetration, so there is no sedimentation of silver or whatever sedimentation metal ion is, and because the fluorescent backing material is not illuminated, so that is not also producing any illumination. So zero illumination gives you really white locations and larger illumination, one layer of illumination coming from the X-ray photons, and then a secondary illumination coming from the backing material of the fluorescent material, giving you a second set of illumination. Together they can give you a much higher contrast value. So like I said, that black parts are made more black and white parts are made more white. Not being racist, just making lecture, so be careful. So that's how we can increase the sharpness of the image and contrast as well. And then we have the idea of CT scanning getting started. So what you can see over here, that the entire idea of the X-ray production is all theoretical. There is no math over here. There will be some math for the CT scanning, which we'll have a look today, or maybe we'll look at it tomorrow. I don't know. But anyway, any questions so far? I'll take questions from the X-ray beam part over here.
Sir, very first ওয়েটা কি জানি বলছেন আপনি একদম শুরুতে, যেটা করে কন্ট্রাস্টটা বাড়ানো যাবে?
For digital X-ray, we can increase it from the software.
আচ্ছা, আপনি অন্য কি জানি এটা বলছেন, আপনি অ্যাপারচারের ব্যাপারে বলছেন বা কিছু একটা।
না, অ্যাপারচার কন্ট্রোল হচ্ছে এটা। অ্যাপারচার কন্ট্রোল করে আমরা শার্পনেস বাড়াতে পারবো, কন্ট্রাস্ট না।
হ্যাঁ, ওইটাই বলতেছিলাম, মানে আর কি অ্যাপারচারটাকে ছোট করে শার্পনেস বাড়বে আর কি।
এক্স্যাক্টলি।
আচ্ছা, সো লাইক যেগুলো পার্শিয়াল শ্যাডো ওগুলাও ক্লিয়ারলি আসবে।
পার্শিয়াল শ্যাডোটা মানে আমাদের এইম হচ্ছে পার্শিয়াল শ্যাডোটাকে এলিমিনেট করা। দ্যাটস আওয়ার প্রাইমারি এইম। তো and partial shadow eliminate করার একটা বুদ্ধি হচ্ছে অ্যাপারচারটাকে ছোট করা যাতে করে আমাদের partial shadowটা primarily less thin হয়, and secondary way হচ্ছে using a collimator so that we can only allow the parallel beams and all the angle beams are not allowed, so that you can have a good borderline.
Yes, sir.
So two different ways are discussed over here to increase the sharpness. একটা হচ্ছে aperture contour, which is this thing, and also then the second one is using a collimator. Any further question? বুঝা গেছে কিনা up so far?
স্যার কলিমিটারের ওয়ার্কিং প্রিন্সিপালটা একটু বলতে পারবেন?
Collimator is basically like let me just show you. Collimator is basically, let's say, like this honeycomb structure, like this, but think about it, which is pretty long. Pretty long means not only of this thickness, they consider it to be significantly long, maybe something like this. So whenever we'll be sending extra beams through here, all the extra beams which are parallel to this structure, okay, they can paint it pretty easily. But if you are sending some extra beams which are coming at some angle, they'll hit the inside border of this metal structure and get absorbed in the collimator. So the hole size and the depth of the collimator, the length of the collimator holes, they are maintained in something like this honeycomb structure. They are maintained in such a way so that we can allow extra photons with an acceptable amount of angle variation. All the extra beams which are going to be passing through the collimator and eventually be coming on the other side will not be essentially parallel, but they will be almost parallel, because the higher angle beams would get absorbed in the inner walls of the collimator.
স্যার এটা কি তাহলে বোথ কন্ট্রাস্ট এন্ড শার্পনেস দুইটাকে ইমপ্রুভ করছে নাকি
No,
জাস্ট?
collimator is usually used exclusively to increase the sharpness. It is practically reducing the contrast because it is actually absorbing a significant number of extra photons which would otherwise be placed on the extra film. Extra film যদি extra beam গিয়ে হিট করে তার মানে কি ব্ল্যাক লোকেশন গুলো আর ব্ল্যাক হওয়ার কথা, ডার্ক হোয়াইট লোকেশন গুলো বাই কন্ট্রাস্ট আর হোয়াইট থাকার কথা. But so collimator practically enhances the sharpness, and it somewhat reduces the contrast, but we don't usually discuss that it's negative effect because we have other ways to increase the contrast. বুঝতে পারছি?
ইয়েস স্যার।
Good. Anything else? Anyone? Question?
Sir, do they ask questions about why do we use a long collimator?
No, not that I have seen. Sometimes they ask what is the purpose of the collimator, and it's a very simple answer, maybe 1 or 2 marks. The wording is usually pretty simple. I described it in detail so that you could visualize the thing. That's why I went through this much trouble, so you could logically make sense that what is actually happening.
Yes, sir. The sharpness contrast parts are easier to understand than the spectra parts.
Well, different people of us, I mean, we all have different levels of our brain working differently, so I totally agree with you, but there is nothing that I can help with you except for recommending that study more. That's just
When I try, sir,
Yeah.
I'm so tired.
It's all right. Try your best and not anymore. Whatever your best is, make sure you should be able to tell yourself that I have done my best, period, and now I'm going to sleep and have a good night's sleep. No big deal. Watch cartoon, play video games, whatever. Make sure that you can tell yourself without lying towards your own self that I did my best, and that's good enough for every one of you. You don't have to do more than what you can do. No, never. All right. I can start the CT scanning today. Actually, CT scanning is pretty interesting. Should I?
Can we do it tomorrow? কারণ এগুলো একটু
হজম করা দরকার।
হ্যাঁ স্যার এটা প্রসেস করতে একটু টাইম লাগবে।
আচ্ছা ঠিক আছে, সমস্যা নাই। We can start this tomorrow, and I have 2 lectures in my computer which I did forget to upload. I'll definitely upload right now, and then we'll start this part next class. Please, thank you very much. বলো।
স্যার আপনি যে বলছিলেন থার্সডেতে ক্লাস হয় না, ওই দিন ক্লাস হয় নাই আসলেই? মানে
বলি ওই দিন থার্সডেতে আমি মনে হয় 10 মিনিট না 15 মিনিট পড়াইছি। পড়ানোর পরে হচ্ছে আমি যেখানে পড়াইতেছিলাম I was not in my coaching, I was somewhere else. আমি ওইখানে ঘুমাই গেছিলাম। So তারপর ঘুমের থেকে উঠে আমি দেখছি যে like it's really late. That's essentially what happened. So I did not go forward with any significant amount of lecture volume that demands lecture upload.
আচ্ছা স্যার ঠিক আছে, তাহলে কি শুধু লাস্ট ওয়েডনেসডে আর
এরপর হচ্ছে
গতকাল
গতকাল এবং
lecture টা?
আজকের হ্যাঁ এই লেকচারগুলো আপলোড করে দিব।
আচ্ছা ঠিক আছে।
ওকে, আল্লাহ হাফেজ পোলাপান, থ্যাংক ইউ ভেরি মাচ, গুড নাইট, হ্যাভ ফান and keep memeing.
Okay, sir. Bye, sir.
Bye.
Good night.
Bye, sir.